Welcome back. I will now do a presentation on capacitors and capacitance for those people in a chemistry degree doing instrumental analysis and things like that. Okay. So what is a capacitor? Well, a capacitor is an item that's in the circuitry of a battery that's able to store charge. Okay, and later on we'll find that charge can actually be useful in terms of doing different things that are useful to us in a lab. Okay, and the way you'll see the capacitor denoted is, you'll have your circuitry like this, and then you'll have these two parallel lines, okay, of equal length, and then of course this will continue like this. Okay, this thing right here, where you have these two parallel lines separated by space, that's your capacitor. Okay, so this is your capacitor. Okay, and so the way you know a capacitor is you'll see that both lines are of equal length and parallel to each other. Okay, again, that's not the same as this, where you have one line that's longer than the other, right? This is actually denoting the terminals of your battery, okay? And oftentimes they'll put a V next to it, okay? That's the terminals of the battery. The capacitor is denoted with these two lines of equal length, okay? So what is a capacitor useful for? Well, it's useful for storing charge. So what we can do is we can charge the capacitor, and that causes it to store energy, and then we can use the energy to do useful things for us, things that the machine is built to do. Okay, so let's actually talk about the structure of a capacitor. Okay, so what you'll have is, and I've drawn this capacitor here, and these red plates that I've shown here. These are two plates. There's an upper plate and a lower plate, and those two things are usually metal plates, and they have the ability to conduct electricity. Okay, but in between the plates, there's space where you have a dielectric substance. And a dielectric substance is a substance that contains virtually no charged species. There's no mobile current-carrying molecules. And so in some cases, it's just a vacuum. But in other cases, you can actually have insulating substances. And certainly a vacuum is insulating. Okay? So basically what we'll see is that electrons can hit one of the plates, and that will actually repel the electrons from the other plate, okay? And that actually builds up an electrical potential between the two plates, and that's actually what contributes to the charge, okay? And so this dielectric substance, okay, will basically not allow electron transfers between the lower plate and the upper plate, or vice versa from the upper plate to the lower plate, okay? And what we're going to do later on in this video is we're going to define a constant, and that's called capacitance. Okay, capacitance for a given capacitor is a constant, and as we'll find, it's actually proportional to something called the dielectric constant, which is this epsilon right here. It's proportional to the area of each plate, right? But it's inversely proportional to the distance between the two plates of the capacitor. Okay. And as we'll find, the higher the capacitance you have, the higher the charge that you're able to store, the higher the charge max. Okay. So without boring you any further, let's actually look at two situations that we can have in terms of our battery. Okay. And again, right here, these are basically the terminals of our battery right here. Now, let's say, for instance, that we're looking at this little circuitry right here. Let's say that this switch S, okay, let's say that it's switched into the 1 position, okay? So that means these two points are going to be connected in the circuit, okay? Now keep in mind that there's electrons in the negative terminal, and let's actually follow the motion of electrons through the battery, okay? And this is only assuming that we are switched to the 1 position, okay? So electrons are going to be moving this direction, and they're going to go here, right? And they're basically going to go here, and then they're going to move up through this resistor. Okay, so right now what we're doing is we're looking at the motion of electrons during switch 1. So they're going to go through this resistor, right, through the resistor, and then they're going to come up here, and they're going to hit the lower plate. Okay, they're going to hit the lower plate, which technically does conduct electricity, but because there's a dielectric substance in between the two plates, you won't have electron movement through there because there's no charge-carrying species in there. Okay. Now, if you imagine what's going to happen at the plate, right? Here's our plate, right? If you imagine what's going to happen, initially on the lower plate, what's going to happen is you're going to build up a lot of negative charge, right? Because there's a lot of electrons flowing that direction, right? And initially there were some electrons on the upper plate, but because these electrons on the lower plate, because they would repel the electrons on the upper plate, the electrons up here, they're going to move away from the upper plate, okay? And in the context of this particular circuitry, they're actually going to move towards the positive terminal. So these purple arrows are denoting the direction of electron movements basically from the upper plate. And this is only the case when you have it switched into the 1 position. So basically, the electrons will flow from the negative terminal of the battery up through across the resistor and hit the lower plate. The electrons, though, can't move across the dielectric substance, but they can repel the electrons that were on the upper plate, and so those electrons will move towards the positive terminal of the battery. Now, initially, from a very instantaneous point of time, you're going to develop a current across this capacitor, right? But that current is going to decay exponentially with time, and eventually you'll lose that current, okay? But what you develop is a potential difference, okay? So you can imagine that we're going to have all these electrons on the lower plate, okay? All the electrons over there, and they're coming from the negative terminal of the battery. But as the electrons move away from the upper plate, you're going to develop some positivity right here, some holes, right? There will be some positivity. And what have we done by ejecting the electrons from the upper plate towards the positive terminal? Well, we've essentially created a potential difference. We've created a potential difference. And with that potential difference, we say that the capacitor is charged, okay? And then we can use that charge to do different things like work and so forth, okay? But basically, when we have this potential difference, we say the battery's charged, okay? And what we're going to find is that if we switch it into the 2 position, we'll actually discharge the battery. Okay. Now, what I can do is I can do just that. I can instead of having it in the 1 position, I can actually switch this into the 2 position. Now, what's going to happen if I do that? Well, what we're assuming at this point is that we already have the capacitor charged, right? Well, essentially, what's going to happen when I move it into the 2 position is the electrons that were on the lower plate. Now what they're going to do is they're going to move backwards across the resistor, right? And they're essentially going to follow up here, right? They're going to follow up here, and then they're going to hit the upper plate. So essentially what they're going to do is they're going to take this other route that we didn't do in the first case. They're going to go down through the resistor, up this side, and then they're going to hit the upper plate, right? So if I redraw this, let me redraw this over here, okay? So essentially what's happening is we have these electrons right here, right? But essentially what they're going to do is they're going to move up over to the other side, right? Now we had positivity right here, right? But essentially what's going to happen is the electrons that were on the lower plate, they're going to instead come up here and they're going to fill the holes that were initiated by the electrons moving towards the positive terminal. So what happens when you take these electrons from the lower plate and move them to the upper plate? Well, what you're going to do is you're going to eliminate the potential difference. So when you switch this into the 2 position as shown here, right, you eliminate the potential difference, and that's what we call discharging the capacitor, okay? So it loses its charge, okay? Now, one thing that's interesting is actually what you can do is, and I'll draw this here, let's say that we don't switch it all the way to the 2 position. Now, what we can do is we can just have it, up right here, and essentially we're not going to discharge the capacitor, but as soon as I move that switch into the 2 position, it'll discharge, okay? So what this means is that you can actually have a capacitor that can store charge for a certain period of time. And as we'll find, the voltage across the capacitor, like the current, also decays exponentially with time. So you can't store the charge indefinitely. It will decay as well, and we'll talk about why that is later in another video. But suffice it to say, you can store charge there for a period of time until it decays. Or you can just switch it to position 2 and it will discharge. Okay? But the overall utility in charging a capacitor is that you can use the energy that's derived from that in order to perform work. Okay, now let's actually go back to our original picture of the capacitor. Okay, so here is our capacitor right here, and we have 2 plates, right, that make up the capacitor with a dielectric substance in between them, and we have a certain distance d that separates the 2 plates, and then of course each plate has a specific area. Okay, now what we're going to do is we're basically going to define capacitance right here as this. Okay? Capacitance is going to be defined as the dielectric constant multiplied by the area of the plate divided by the quantity 4 pi d. So what does this mean? Well, the capacitance is actually directly proportional to the dielectric constant in the area, but inversely proportional to the distance between the plates. Okay, well, what was capacitance to begin with? Well, it's a measure. It's basically a measure of how well the capacitor is able to store charge. If you have a higher capacitance, you can store more charge, right? And actually, as we'll find, the charge is actually also directly proportional to the voltage. And in fact, what we'll find is that the charge is actually equal to the capacitance times the voltage. Okay, but for now, let's just worry about the capacitance. So it's equal to epsilon A divided by the quantity 4 pi d. Well, let's kind of reason our way through this, right? Okay, the capacitance, the ability to develop a charge or a potential difference across the capacitor is proportional to epsilon, which is the dielectric constant. Okay. Now think about this. If you have a high dielectric constant, okay, that means that you're more insulating, right? And if you're more insulating, you don't allow electron movement across the capacitor, right? So if you're allowing less charged movement across the capacitor, right? If there's less charge going from the lower plate to the upper plate, you're going to develop a higher potential difference, and therefore you're going to have more charge. Okay, so the higher epsilon is, the more capacitance you have. Okay, and I think that makes sense, right? As you increase the insulating nature of that substance, you develop a higher potential difference because there's less ability for charge to move across the plates. Okay. Also, the capacitance is directly proportional to the area. Okay, if you have more plate, right? If you have more plate, there's more electrons reaching the plate, then there's going to be more repulsion of the electrons from the upper plate towards the positive terminal, right? Because there's more area for those electrons to hit, and therefore, if there's more electrons, there's more repulsion of the electrons from the upper plate, and they will move towards the positive terminal, right? But the capacitance is inversely proportional to the distance between the plates, and I think that makes sense, right? If you have two plates that are farther apart, right, the electrons that reach the lower plate, they don't have as much repulsion to the electrons on the upper plate, right? Because there's a higher distance between the two plates. So if you have, say, if you have two plates that are, say, I don't know, abstract quantity of 3 apart, right? There's going to be more repulsion there than you would if their distance was 6, right? If the distance was twice it was in the first case, there's going to be less ability to form a potential difference because there's going to be less repulsion, okay? So the higher the distance is between the two plates, the lower the capacitance is, and the worse you are at developing a potential difference, and you can store less charge, okay? Because keep in mind that charge is equal to the capacitance times the voltage, okay? So hopefully at this point we understand a little bit about capacitance and how you could calculate it, assuming you know these things, okay? But in general, what we can say is this equation right here is that the maximum charge that a capacitor can store, is equal to the voltage across the capacitor times the capacitance, okay? And whenever you see these capital letters, in the case of Q and V, that just means we're talking about basically the maximums or the initials, okay? When you see the little lowercase letters, that's implying that we're talking about instantaneous versions of those quantities, okay? So we can say that the maximum charge is equal to the capacitance times the maximum voltage across the capacitor, okay? But we can actually look at instantaneous versions of those quantities. Let's say that we have an instantaneous charge Q, which is going to be equal to the instantaneous voltage across the capacitor times the capacitance. And keep in mind that the capacitance is just a proportionality constant, okay? For a given capacitor, right? For a given capacitor, okay, we're not changing the dielectric substance, right? So the dielectric constant won't change. We shouldn't change the distance, and the area is going to be constant. And since 4 pi is also a constant, that means C is a constant as well. And in these equations, it's a proportionality constant between voltage and charge. Okay, but let's do something further. Let's actually express the left equation in terms of differential notation. Okay, so what we can say is that dq, an infinitesimally small change in the charge, is equal to C, the capacitance, times an infinitesimally small change in the voltage across the capacitor. Okay, so that's good. But what we can do now is we can divide both sides by dt, right? Let's say we have a charge that's changing with time, okay, and that would be proportional to a voltage that's changing with time. So if we do one thing to one side, we have to do it to the other side, okay? And now what I've done is I've said that an infinitesimally small change in voltage that changes with time is proportional to an infinitesimally small change in charge with respect to time, okay? And I think that makes sense, right? And it's proportional through this C, okay? And actually what the dq dt is that's the instantaneous current. So what we can rewrite this as is the instantaneous current is going to be equal to the capacitance times an infinitesimally small change in voltage across the capacitor with respect to time. Okay. Now, one important thing that comes out of this is what happens if we have a voltage that's not changing with time? Well, if we have a voltage that's not changing with time, in other words, it's time independent, what's the change in voltage? Well, it's zero, right? So if you have a voltage that's not changing with time, dV dt is just zero, right? So in that case, the current would be zero. So in other words, if you have a voltage that's not changing with time across the capacitor, the instantaneous current is going to be zero, okay? So I hope that makes sense. Okay, and basically what we're going to do in the next video is we're actually going to talk about the exponential decay of some of these quantities, such as the current, the voltage across the capacitor, and the voltage across resistors. So I hope this video gave you a little bit of intuition on capacitors. See you in the next video.